Good evening, all. You're all welcome to this channel. This Good evening, all. You're all welcome to this channel. This channel is Computer Science University, and this science is all about teaching you the course content you find in your university if you are studying computer science. So, you're welcome. You're permitted to share and invite others to be part of this learning community. Today, what we have before us is a major important part of the computer. The last time we looked into the computer system and I showed you a few number of things about the motherboard. So today this is a typical motherboard. And so we said that the most important part of the computer is the processor. So for a typical, this is a motherboard and this is the electronic component of the computer. This is the electronic component of the computer. So this is your processor. This is where you have your processor. So all about here is the processor and its sockets. So I have another board here, and in this board, this particular board should give you here also you have your processor. This is your processor socket, and these are other components of the board. So you have this all right here, so you can see them. Okay. I have more than one board here, but for the sake of this lesson, I'll quickly take you through what we have for this course. Okay, so processors generally is a generic name. Processor is a generic name. Generic name in the sense that something processor is from the word process. So remember, we define a computer as an electronic machine that receives data and then transforms this data into information. It processes the data and then transforms. So processes and delivers the results of the processed data as information. So what is responsible for this processing? So that is what we want to look at today. We want to look at the most important part of the computer, which is usually called the brain of the computer, just like I've shown you here, the brain of the computer. It is called the processor. But typically for a computer, we call it CPU. CPU there stands for Central Processing Unit. CPU stands for Central Processing Unit. Okay, so let's see what we get to learn from here. The CPU is the brain of the computer system and it is called the Central Processing Unit. So this part of your motherboard is called the Central Processing Unit. This is the Central Processing Unit, this particular part. I'm sure you can see this part here. This part where you have this square. This is your motherboard, and the part you have the square here. Here is where you have your processor. Okay, so modern CPUs would come in cores. Modern CPUs will have more than one core. When I mean more than one core, would have more cores inside the processor. For example, what I mean by more core is you have systems appearing as core i5, core i7. It means they have multiple processors in them. For example, they can take advantage of parallelism. What I mean by parallelism is tasks having each of the cores having to handle different tasks at the same time. So multitasking and multi-cores inside one processor. So let's move ahead. We'll look at also generations of the CPU. To some course content, it will be generations of the computer. But I'm taking it as generations of the CPU because there are various aspects of this. If I want to take generation of computer, then I have to be looking at the various evolution across memory, across storage, across the input-output devices and all of that. But for today, we just want to look at the generations of the CPU. The first generations is when the CPUs were built with vacuum tubes. Then you have a whole large system. you have a whole house standing as a computer. So, but as evolution continued, we now had the second generation computers. These second generation computers use what we call transistors. So a typical transistor is what you see on your screen right there. So you have thousands of transistors to make a computer. So in the third generation computer, you have integrated circuits. So integrated circuits are where you have ICs. You have multiple ICs, just like you can see on the screen. You have this CPU made up of ICs. Okay, let me take you a bit into this. Let me take you a bit into the CPU. This is the CPU. You would usually have a cover on it, just like you have here. You can see a cover on it. This is a CPU cover. One of the reasons, this is also a kind of protection for the CPU. However, for some kind of CPU, you will not find this cover because of heat, like in AMD processors. AMD processors do not have this kind of cover because AMD processors get hot after. Remember, I said in our last class that AMD processors are usually suitable for Western countries where the temperature is not as harsh like in the sub-Saharan Africa. So, like this is the processor would have a retention arm. This retention arm, you press it here so that you can pull it out. It's out, and so you see you have this part of the processor. I remove the retention arm, and you can see the processor is just a chip. Look at the processor. Processor is just a chip. So this processor goes to the processor socket. So this is the socket for the processor. You can see there the socket. This is the socket for the processor, and this is the processor itself. So this is the processor, and this is the part that is connected to the processor. Okay, so I just unmounted the processor, and I'm going to mount it back. Okay, so I'll mount it back. While mounting, I'll need to fix back the retention arm. I'll need to fix back the retention arm after mounting. So I'm taking this opportunity to show us what the processor looks like, and so this is all what we're going to be dealing with today. We're going to be dealing with this singular part of the computer, which is called the processor. Okay, so everything I'm talking about today is the processor. Remember, I'm still on the generation of computers, and so I was telling you about the third generation computers and the computers that are made of ICs. Computers that are made of ICs. So that's the fourth generation computer. So some CPUs will have loaded and more integrated circuits to just form a small chip like this. So in a chip like this, you could have, say, 5 cores, 4 cores, as the case may be, depending on the type of processor you're using. This is just an introduction to show you what a processor looks like, and there are other components of the computer we may not be talking about today. Like this is a RAM. This is a RAM, random access memory. Remember the last class I was telling you about a RAM. This is one of the electronic devices inside the motherboard of your computer. So this is a RAM, and it's used to store the on-the-go instructions. What I mean by on-the-go instructions is I mean instructions that are ready to be used up by the computer at that running instance. So they are stored in this kind of chip. This is random access memory. Okay, but today we're focusing on the processor. So I just made an introduction so that we can see the generations of processor. It's now time for us to look at the CPU itself, the working of the CPU. Okay, so it's important that we talk about the von Neumann model. The von Neumann model. This von Neumann model is an architecture. Von Neumann is a man that designed the architecture of the computer. He designed the architecture of the computer, and while he designed the architecture of the computer, he was able to partition the computer into three major parts, which is the data processing unit, also the program control unit, and also the memory. So but usually you would always see most architecture of a computer, you see most architecture of a computer divided into the control units and the arithmetic logic units. Actually, it doesn't mean they are wrong, but what it actually means is that's the way the person perceives the computer to be. But for the sake of teaching, and I'm sure it conforms to what you use in your school, especially for the sake of introduction, I'm going to use the von Neumann model. I'm using the von Neumann model because it's not a complex architecture. When I mean architecture, a complex, how you view the CPU. So the architecture just describes, in this case, a diagrammatic description of how you see the computer. So like I said, the CPU is usually located at the center. You find the CPU is that square-like chip at in your motherboard, just like what I showed you here. Okay, so and we also know that one of the main functions of the CPU is the CPU interacts with other parts of the board. For example, this is where you have, this is your RAM slot. This PC has two RAM slots. This blue line here is your RAM slot. You see, this is RAM slot 1 and this is RAM slot 2. These are the two RAM slots. Okay, for this PC, it has two RAM slots. So this CPU, the CPU communicates, this CPU communicates with the RAM, it communicates with the hard drive. The hard drive is where is the external storage parts. This is a hard drive. Actually, it's not always on board. It has to be separate. It's a separate component. So this is your board, this is your motherboard, and this is your hard drive. This is a typical hard drive for a desktop computer. For a laptop computer, you find microtechnology where you have a slimmer device than this, not as big as this. Okay, so it's the duty of the CPU to communicate with the RAM, to communicate with the hard disk, to communicate with other important parts of the computer. Like there are some other parts of the computer that are on the board that the CPU would need to communicate with. Okay, let's see the working of a processor. Let's see the working of a processor. The working of a processor. Okay, typically, how does a processor work? Number one, the processor executes a collection of machine instructions that tells the processor what to do. For example, human beings give instruction. Humans give instruction to the computer, and the computer executes the instruction the person has given to it. How does the computer execute this instruction? It executes this instruction by receiving the instruction. It decodes the instruction it has received and take it through a series of stages, which we're going to look at. It takes the instruction it receives through a series of stages and then gives the results at the end of the day. So typically that is what a CPU does. A CPU gets an instruction. For example, an instruction could be 2 plus 2 equals 4. 2 is saved in a memory location in your computer. First of all, 2 plus 2 equals 4 is written as an instruction in your own storage. And then what your processor does is through a bus. What is a bus? A bus is a link, BUS. A bus is a link to every part of the computer. Generally, that's what a bus means. It's just a connecting line, a communication line between various components of the computer. So between the CPU and the memory, there is a bus, usually called the address bus. Between the CPU and your ALU, there is also a bus called the control bus. Between CPU and the social memory, there's a bus called the data bus. So these buses are just communicating lines. That's where little informations or little data go through from that component to the CPU or to and fro, whichever it is. So let's look at the major, based on instructions. A microprocessor does three basic things. Number one, it performs mathematical operation. When we mean mathematical operation here, we don't actually mean calculus. We don't actually mean set theory. We don't actually mean maths. So you shouldn't be scared. But we just mean anything that has to do with mathematics in what you are doing, because the computer reasons like a human and it does a lot of plus and minus. So after it does the basic mathematical operation, what it does is it process and transfer data. Another thing is it also makes decision. So these are basically what the computer, what a processor would do. But now, this is just a summary of what a processor would do. Would like to see basically what a processor would do, like in stages. Like we want to see a systematic running of what a processor would do. Okay, let's get to see the systematic stages of what a processor would do. The systematic stages of what a processor will do. Okay, sorry, I'm still going to be making reference to the von Neumann architecture. I'm going to be making reference to the von Neumann architecture because I will be explaining quite a number of things from it. Okay, the first thing the processor does is it fetches instruction. Instruction is, where's the instruction coming from? The instruction is coming from you, it's coming from me, it's coming from user, the user of that system. So what the system does is it gets instruction. We call it fetch. That is the language of the CPU. We say it fetches. Fetches in the sense that the instructions are not in the CPU. Where's my CPU? The instructions are not here. This is the brain of the computer. Fine. This chip you're seeing here is the brain of the computer. But the instruction that makes this brain functional, the mind of the computer, or how do I put it? The mouth, the ear, and other receiving part of the computer is not here. This is just like the brain of the computer. So there's need to fetch instruction. There's need to fetch instruction. After the instructions are fetched, the next thing is these instructions are decoded because they are written in human language. For example, human language, languages that are meaningful or understandable by humans. For example, I can say, okay, I want to fetch. Okay, how do I want to give you an analogy now, a kind of language, a human-made language, because there's a difference between a human-made language and a computer language. A human-made language could be, okay, how do you find, say, the area of a circle? Area of a circle is, you say, okay, let A be equals to pi r squared. Let A be equal to pi r squared, and get the value for A, get the value for pi, get the value for r, multiply together. All this I'm saying is human language. But the computer doesn't understand human language. Why? Because each of these processor, before it is made, what makes this processor is the instruction set for every processor. The manufacturers of processor has made what is called an instruction set for every processor. So this processor I'm holding has its own instruction set. That is, the instruction set is all the possible instructions in machine language that this processor will understand. So if the instruction you are giving to the computer cannot be matched with the instruction set, this guy will not be able to execute the instruction. So there's need for decoding information. It's actually complex, but I'm giving you the summary and the tip of it. Okay, the next one is it performs ALU operation. Performing ALU operation. ALU means arithmetic logic unit. That's a part of this processor. The ALU part handles anything that has to do with plus, minus, times, division, anything that is logic, and or NAND. Don't worry, in our next lesson or so, in one of the lessons, we are going to look at logic circuits, we are going to look at logic gates, and we're going to look at logical operations of uh, how the CPU does logical operations. Okay, so that's by the way. The next step is it performs, okay, it accesses memory. After it performs the ALU operation, it accesses memory. That is, you need to go back again to memory and get some information from memory. Like one of the information you get from memory, the CPU gets from memory is the program counter. That is the counter. The counter is for every computer program, you have a particular place. You have a particular place, a particular line where instructions, the current instruction being executed is hold. There's something called line number. Okay, I can also show you from my, let me show you. I would like to show you what I mean by that, because it's also very important so that you understand one of the how program counters, okay, how program counters are made. Okay, let me take you through a simple program here. Simple program. I want to take you through simple program. Okay, this is my notepad interface, and so let me change my language to say, okay, let me just use a very simple language. Let me use language that is okay. It's just a language, just to show you what I mean. Okay, look at me now moving through the text editor. You can see the numbers changing 1, 2, 3, 4, 5, 6, 7, and you can see me on line 14. For example, if my line 1 is okay, open memory, or let me use load memory A, load memory B, say create memory. This is not a language. I'm just giving you a pseudocode to make you understand what we're talking about. Load memory, create memory C, add B to A, add B to A, put result of line 4, let me call it L4, put result of line 4 into C, and then say display C. Okay, display, okay, let's call it load C, possibly print C. Okay, now it's important that during this kind of programming, as the processor is moving across each of the line, you will notice that as the processor is moving along the line, you will notice there's something you're going to notice. You're going to notice that you'll be moving from one line to the other. You'll be moving from one line to the other. So it's therefore important for you to let the computer know the last line you have moved, the last line where the instructions are being executed. For example, you just loaded memory A. You have to be telling, what you have to be doing is you have to be telling your program counter, that you have left you are done with line 1 and you are now about to move to line 2. So the computer needs to be informed at every stage that you have left this part and you are now moving to the other part. So you need to access memory where the line numbers, you call it, there's a special memory in your CPU that is called the PC. Here you're looking at the PC right here. PC is under the programs to control unit. There's a register there named PC. If you're looking at the von Neumann model there, you are going to see PC. The PC there is the program counter, and so it's a memory inside the CPU. So you need to access that memory at that point in time to be able to now communicate which stage you are in executing the instruction. Okay, let's move ahead so that we can get this concept very well. Okay, that's the von Neumann model. Now let's move into the stages in detail. Okay, now this is what we have in the stage, or what I've been trying to explain. The first thing to do is to fetch. You fetch the instruction. An example of an instruction is this. This is just an instruction. This is how computer instructions are presented. These are saved in your memory and the CPU will access it from memory. So this is an example of an instruction. So what during the fetch, what happens during the fetch is human languages are translated into computer languages. What are computer languages? Computer languages are made up of just 2 digits, 2 switches, zeros and 1. Usually they are called the base 2 numbers and they are binary numbers. So let me show you what happens during the fetch from this little pseudocode I've written. So during the fetch, maybe this load A could just be 0000 11111 000011, and for the second one it could just be say 1010 1010. I'm just giving an instance of what it could be. Block 0000 11111 0001111. So that is like we are giving the machine equivalent of that line. Okay, so when we now move to the next line, so you have something like this again. Say the next line could just be 0101 0000 1111 1111, and like that. Okay, let me take you to what I'm trying to do here. Now, during the fetch, what the system is doing during the fetch is it fetches it from memory, and then the next thing it does is it decodes it. So during the fetch, what happens during the fetch? Look at during the fetch. To execute an instruction, the processor copies the instruction code from the program memory into the instruction register. So there is a register. If we go back to the von Neumann model, you are going to see that. Let me take you back to the von Neumann model. In the von Neumann model, there is a register that is called IR. That is the instruction register. So that instruction register is inside the CPU, and what the instruction register does is it's the program you got from memory. The program from memory is sent to the instruction register of this your CPU. That is, the program from your memory is sent to the instruction register in this chip. Okay, so the program counter stores the address of each instruction. That is, for every instruction, there is the address bits. Every code, every instruction like this, there is the address part is there and the data part is there. So when we go to addressing and when we take the course advanced into computer architecture, we are going to explain addressing and we're going to explain memory locations. Then we'll do a little bit of C++ or assembly language so that we can understand the primitives and data structures in the underlying machine. But let's not go to that. We are looking at the stages, simple stages of how the processor executes instruction. We've looked at what instructions are. You are the person to give the computer the instruction. It's the duty of the computer to decode, to fetch the instruction and decode it. So what happens in the decode stage? In the decode stage, during the cycle, the encoded instruction present in the instruction register is interpreted by the decoder. So there is a decoder in this processor that is responsible for doing the decoding. Because why is there a need for decoding? The computer does not understand what you mean by load memory A or load memory B or create this. It doesn't understand because it is not part of the instruction set of the processor. Every processor has an instruction set. There is no processor. That's why those who make the processor, they already know all the abilities of the processor. They know all what the processor can do. So all what this processor can do is embedded as an instruction set, a set of instruction. It is not the same instruction you are giving. The instruction you are writing, this particular instruction showing on your screen now, this one is not the instruction set of the processor. This is just your instruction, what you want the computer to do. But the manufacturers of this processor already have it's built. There's a predefined instruction set for this that contains all the zeros and one ability of this processor. Okay, let's push it further. The next step is ALU operation. Remember, if I am to take you to the von Neumann model, you see what I have in the ALU operation. The ALU operation in the von Neumann model is this part, the arithmetic and logic unit. You can see it there at the top left. Under the data processing unit, you have the arithmetic and logic unit. Okay, so what happens in that stage? During the ALU operation, this is where two operands in the instructions will be operated on. For example, when you have operations, add A to B, add, look at this add here. You can see add on line 4, add B to A. That is an operation, arithmetic and logic unit. So arithmetic handles the plus, the minus, the times, the multiplication, the division, and all of that. Then you have, that is where the ALU comes in. So here, a simple notice, this is where the two operands in the instruction will be operated on giving operator in the instructions, such as if the instruction was to add two numbers, then here the addition will happen. This is where the addition actually takes place. Okay, the next stage is access memory. Access memory. Now, there are two types of access you can find when the processor is doing its computation. Two types of access. One of the access is moving from memory to register or from register to memory. When you are moving from memory to register or you are moving from register to memory. Okay, just like you have on your screen there. Try to get that up and we have it there on the screen. So there are only two kinds of instruction that accesses memory. This guy only uses two types of instruction to access memory, and those instructions always apply when you are moving from memory into another memory. Is here, that memory is called the register. When you are moving from memory to register, or when you are moving from register, from this register here to a memory, this is when the access memory of the CPU take place. That's when because there's always a movement, a communication between the CPU and memory. The CPU cannot do anything without memory because that is where it gets information, it gets the data it's working with. So there's always a communication line between if you go back to the von Neumann model, you will see you will see an address line, you see a signal line, a communication line between the CPU and the memory. So whenever you are copying from register, the register is a memory that is based in the CPU. So when you are copying from a main memory to the register, or when you are copying from the register to the memory, you access memory. That's the stage. So after accessing memory, what do? There is need to update the register. There is a register called the PC, the program counter register. It's important, and other registers in this your processors needs to be updated. You can see this, the way the CPU works is just like a car assembly line. I want you to look at the CPU, the processor, as a car assembly line. In a car assembly line, while somebody is trying to build the body of the car, another person is trying to work on the engine, the combustion engine, another person is trying to work on the steering, another person is trying to, fit in the gearbox, and from there, all these various parts of the computers are put together to all the various parts of the car are put together to be assembled into a manufactured car. Now this goes through a repeated cycle until the car is produced. The same way the CPU works. The CPU works through the instruction. The instruction is like a loop. When I mean a loop, like you are going around the circle. You are going around the circle. You fetch. After fetching, you decode. After decode, you execute. After fetch, you decode, you execute. Line by line, you fetch, you decode, you execute. I'm breaking this now into three, but it's in the fetch, decode, and execute cycle. There is more to it, just like I've broken it down now. But the short form of all what I've been saying is this guy will be doing this thing for a repeated number of times. Fetch, decode, execute, fetch, decode, execute. That's what the processor will be doing for you. Okay, so it updates the register. In the midst of this communication, the register is always updated, because that's why I said it's a complex operation. But introducing processors to you, I should be able to make you understand the underlying working of the processor. It will also make you appreciate the ability of the processor, of the technology in this processor. Okay, so remember, some instructions, when you are writing your instruction, like in the code we have, at a point um, we said load memory A. There are some points where we needed to branch. For example, go to line 4. I think that's in line 5. In the line 5, we said put result of line 4 into C. So it means at that point, the program will need to go to line 4. So now I made a comment written in red there. I said, for example, when you branch from a line of code to another line, there is no result or feedback from the arithmetic logic units. There is no result or feedback from the arithmetic logic unit. So what it means is that at that point, the ALU would not feed. There won't be any feedback to the register at that point. So that point can be skipped. Now we have the update of program counter. The program counter is a special kind of memory in the processor. Is a register. 2 is a memory in the processor, and there is need to update the program counter PC when a current instruction has completed execution. Remember I said there is repeated cycle. It's a repeated cycle. You fetch, you decode it, you fetch instruction from the user, you decode it. In the decoding, you move it from human language to machine language, and then after that, you execute. During these 3 cycles, there is need to update the program counter, because the program counter is responsible for managing the lines of the instruction. For example, line 1, line 2, line 3, line 4. When you are done with line 1, there's need for the PC, which is the register in your processor, to be updated. So you update your PC, and that's what I was trying to say here. Update your program counter. After updating your program counter, say there is need to update the program counter when a current instruction has completed execution 1 cycle. We need to update the address of the next instruction so that we can go back to step 1. You can see go back. The going back there implies looping. When you are done with the first one, it loops again. That's how the computer does until it executes the instruction and it gives you the required results you want. I want to believe that with this little explanation I've made clear to us, like in this lesson, I want to believe you should begin to think now about how this guy, which is called the motherboard, interacts. First of all, remember I introduced the processor to you to rest in a square-like socket in your motherboard. This is the motherboard, and I introduced what the processor looks like. I told you about the processor, and I said it's a square-like part, and I told you of the retention arm. When you want to remove, you bring out the retention arm, and then you remove the processor. I already removed the processor in this case, and that is what we have here. And I went ahead to explain the functionalities of this processor, how it works. Now, the need for teaching this introductory part is to enable us to appreciate the working of the computer and how this works. This is Computer Science University, and this is a channel created to learn the curriculum of computer science, to go through the course content of computer science outside the wall of the university. I want you to invite your friends who are into computer science and IT so that they can get the grasp, they can get the basic understanding of processors. Just an introductory part. When we go into organization of the computer itself, and then we go into computer architecture, we'll be able to go deep into a lot of concepts. So for now, I believe I've made justice to introducing you to processors. Remember, we have generations of processors. The first generations where they use the vacuum tubes, second generations where they use transistors, the third generations where they use the integrated circuits, and fourth generations where they used digital circuits like multiple cores of processors and the rest of them. I gave you that when we started. I was able to use this illustration to show you that, and I was telling you about having a computer that can have more than 7 cores. It can have more than 7 processors inside the computer. Okay, so I want to believe we have done justice to this. Thank you very much for giving me your audience. I want to believe you have learned one or two. I would like to see your suggestions, and I would like to see your questions in the comment section. I will be willing to answer them. Thank you and bye for now. See you next time. My name is Peter Obike, and I'm your instructor in computer science.